in the rooms, you got light fixtures illuminating the room, and also the lights gives out heat, so that contribute another heat load. And also evaporators are installed with fan to move air around, and so the heat from electric motors will also contribute to the room. And also in the refrigerated facilities or the cold space, you will have mechanical devices like forklift trucks, and then your conveyors and other material handling systems that motors operating them. So the heat from the motors contribute heat into the room as well. And the last one is defrost heat. This is only applicable when it is in freezers, because the evaporators ices up in the freezers, and the ice or frost need to be removed. Otherwise, it's going to impede the airflow through the evaporator. Now, often the heat loads that doesn't occur at a constant or steady rate. The heat flow into the evaporator, just like the heat coming through the walls and ceiling, which is a constant and steady rate. At times there will be peaks, for example, in freezers, when a new batch of warm products introduced into the room, the rate at which heat is released into the air by the warm product will be several times higher than the heat released from products nearing complete freezing. The estimation of the mean or average heat load and the treatment of this mean load as a design load is not always appropriate. The size of the refrigeration must be such that the peak loads due to the warm product can be handled adequately. Hence, if the load is overestimated, an excessively and expensive plant will result. On the other hand, if the load is underestimated, the plant may not perform to specification. Next slide, please, Marie. Now, with the evaporator selections to be installed in the cool rooms or freezers, it's important that the size of the latent and sensible components of the total load are known, because the cooling capacity of the evaporator consists of two components, the latent component and the sensible component. And just recall the definition of sensible heat. Sensible heat is heat transfer involving temperature change. And the latent heat latent heat transfer is heat transfer involving phase change. So in this case here, the sensible heat load is a heat removed at the evaporator by bringing about the temperature change in the air. You got the warm air going in and you got cold air coming out. Now the latent component load is the heat transfer to the evaporator by water vapor turning into condensate water or ice in when the temperature is below zero. Now the ratio of this sensible heat component to the total load is known as the sensible heat ratio. This ratio is a factor in the design of the evaporator coil and the coil selection, because they determine the fin spacing and also the number of rolls on the coil as well. Next slide, please, Mary. Now, number one, the product heat load. The possible loads imposed by products are A, here, sensible cooling. This is involving lowering the temperature above or below freezing. So these loads can be calculated using that formula shown in the slide, which is QS equals MC delta T divided by N. QS being the sensible cooling load, M the mass of the product, delta T the temperature difference, the difference in the initial product temperature and the final product temperature, and C being the specific heat of the product, and N being the product cooling time. Now, if the products need to be frozen, obviously heat need to be removed from the product, and this involve what called latent heat transfer, and the heat load for it, the formula is given, is shown, which is QF equals to M HFC divided by N. And well, Q and M explained previously. HFC is known as the latent heat of fusion of that product stored in the room, and N being the time to freeze the room, the product. Now, the last one, if fruits and vegetables are stored in the room, even the fruits and vegetables are harvested, they're still actually living and they will expire. So from fruits and veggies, we've got another source of heat called the heat of respiration. And the formula for it is shown in the formula here, which is QR equals to MHR divided by 1,000. So now HR here is the heat of respiration of the product. The unit measurement here is shown as watt per kilogram. Hence, we divide by 1,000 as shown in that formula. Thanks, Marie. Next one. Now, the second lot of heat in the room is the heat flow through the room structure, which is the ceiling, walls, and floors. And obviously, this heat is coming in by conduction. And this heat load can be considered to occur at a steady rate. And because this heat transfer involving change in temperature, so it is a sensible heat load. And the formula is again shown here. Q is equal to U by A by delta T divided by 1,000. And A being the surface area of the room, totaling up the surface of wall, ceiling, and floors as well. And delta T is the temperature difference between the inside and outside temperature, measured in degrees C or K or Kelvin. And U is the overall heat transfer coefficient of that structure, the material construction. Now, next slide, please. Thanks. Now, if the structure is, say, the wall, floor, ceilings of one single material, the U value is given by the formula shown here, which is 1 divided by the sum of 1 over HI plus X over K plus 1 over HO. Now, HI being the inside surface conductance, measured in watt per square meter Kelvin or degrees C. HO is the outside surface conductance, again, same unit of measurement, X being the thickness of the insulating material, which is measured in meters, and K is the thermal conductivity of the material. Right, next slide, please. Marie. Now, in practice, the walls and ceilings and so on are made of composite materials. So if there are 3 different materials, here the formula shows you the formula for the U value. This formula now has added the X over K for 3 different materials. All right, we'll go on to the next slides. I hope I'm not going too quickly. Now, the third type of load imposed on the evaporator will be the heat output of people working in a room. And this heat output will increase if the temperature is lower. And also, if the dependent on the activity of the person in the room as well. So it's more active, more heat output from the person. Now, even the people working in the room as well wrap up in warm clothing, the occupant will also exert a considerable heat load, mostly in the form of hot breath, especially in freezers. Now, this load can be considered as a latent heat load because of the water vapor coming, from the hot breath, and also considered as an average or mean load. And the typical value for all conditions is often taken as just one value, which is 350 watt per person. So hence the formula Q is 350 by N divided by 1,000, N being the number of people in the refrigerated space at any time. And as I say, because you've got 350 watt per person, that's what we divide by 1,000, the load being in the units of kilowatt. Next one. Now, the fourth one being the air interchange heat load. Now, air interchange is a term used to describe the replacement of the cold air by the warm air from the outside when somebody opens the door. The entering outdoor air will contribute both sensible heat and latent heat. And the latent heat will be released on the evaporative surface by the form of condensate or ice forming on the evaporative surface. Now, this heat load can be considered as an instantaneous or peak load, or just as an average load. So the formulas for both. The next one shows you the formula. Marie, please. Next one. Now, if this air interchange heat load is taken as an average load, the formula is shown again on this slide here. Q being the heat load due to air interchange, V being the average air velocity entering the room through the door, and A being the door opening area. And HO here now, even though we used it previously, now HO represents a different thing here. HO is the entropy of the outside air, and HI, the entropy of the inside air. Previously, HO was the surface conductance. Unfortunately, we use the same symbol. And rho I being the density of the inside air, and uppercase DT being the decimal portion of the time the door is open. Next slide, please, Marie. Now, if the instantaneous load due to interchange is considered as the source of the heat load, the formula is shown here. Q, which is load due to interchange of the peak heat load, is the sum of the V door plus V traffic, and rho I, which is used previously, and same thing, HO, HI. And V door being the volumetric airflow rate through the open door, and V traffic being the volumetric airflow rate due to the forklift entering the open door. Next one again, Marie. Now, air injection is one of the main sources of water vapor into the refrigerated space. And this load influences the RH or relative humidity in the refrigerated space. Sorry, my phone has been, sorry about that. Now, the RH in turn influences the amount of water removed as condensate or as frost on the evaporator. Next one, Marie, please. Now, the fifth one, heat loads due to electrical and mechanical devices. The first one we consider is the evaporator fans, and the heat is coming from the electric motors driving the fan, and these can be a major source of heat load. Now, in blast freezers, where you got very high air movement and large motors are used to move high volume of air, the heat load just from the evaporator fans could be as high as 1/3 of the total load. And remember, in this case, we need the cost of operating the fans. There's the operating cost plus you got the that heat load due to these fan motors, which increases the size of the refrigeration plant, meaning you also will increase the running cost of the refrigeration plant as well. Hence, we're paying for it twice. And that could explain why with snap freezing a product is to save energy to go from blast freezing to plate freezing, where you eliminate that source of heat into the room. Now, air movement is required to transport the heat from the various sources in the room to the evaporator. And the rate of air movement is highly influential in that rate of heat removed from the product. Now, high air movement, the higher the number of air changes, allow the freezers and cools to be more compact and kept the cost to be reduced, although at the expense of higher fan operating costs, of course, and running costs too. Next one, please, Marie. Now, this fan heat load can be calculated as shown in the formula here, and Q being the load due to the fans, and V being the fan volume flow rate, and delta P the fan static pressure, and the Greek formula eta, and F being the combined fan and motor efficiency. And the reason dividing by 1,000 because the basic unit turns out joule per second. That's why we need to divide by 1,000 to give us kilowatt. Next one, Marie. please. Now, lights. Light fixtures produce two forms of energy. In terms of illuminating the room, and also the energy also contributes sensible heat into the room. And again, if say the light source of incandescent or fluorescent light, that could be a high source of heat. Hence, nowadays, by using LED lighting, they will reduce the cost as well. Remember, like with fan, we pay for it twice. One, running the cost of the light, and then again, increase your running cost of your refrigeration plant. Now, heat loads due to lights is, again, the formula is shown here on the slide. Q being the load due to light, and L being the number of light fixtures, and WL being the wattage of each light measured in watt. This will again divide by 1,000. The heat load, we use a unit of kilowatt. The next one, please. Now, when the cooling medium in the evaporator is a secondary refrigerant, not a primary refrigerant, and also if the refrigerant for the evaporator is pumped in, such as in liquid overfeed system, the heat in the secondary refrigerant or the pump refrigerant has a heat coming from the electric motor, delivering that refrigerant to the evaporator. Now, with other mechanical devices, such as forklift trucks, process equipment, conveyors, and other materials handling system, operating the rooms will also produce sensible heat due to the motors operating them. Now, Marie, next one, please. Now, the heat load due to motors of pumps, forklift trucks, process equipment, conveyors, and so on is shown by the formula here. Q equals NM, and uppercase M, and M being the number of motors of equal ratings, and uppercase M being the normal motor rating. This time measured in kilowatt. That's why we don't divide by 1,000. Yeah. Next one, Marie. Now, the last one is only applicable to freezers, because in freezers, the need to defrost evaporators. And defrosting evaporators using some of heat source will impose an additional load on the refrigeration system. The rate of frosting on the evaporator is directly related to the latent component of your total heat load. Now, the higher the latent component of the total heat load, the more the frequent defrost will be required, and higher of this defrost heat load as well due to defrost. Because to defrost the evaporator, heat is added by either electric element or hot gas or warm water to melt the accumulated frozen ice, which is then drained away out of through the condensate drained out of the refrigerator space. Next one, Marie, please. Now, to melt the frost, a large part of the metal of the evaporators, coil, and the associated piping must also be heated. Cooling this mass of heated metal down to normal operating temperatures exerts a heat load on the refrigeration system. And this heat load due to defrost is shown by this formula here. Q equals to 0.13 Q T-lag multiplied by 1 over eta D divided by eta D. And Q being the load due to the defrost, Q T-lag being the total average the latent load component of the total heat load, and eta D being the defrost efficiency. And for water defrost, that value is 0.3, and for hot gas electric defrost is 0.2. I think this is the end of presentation, ladies and gentlemen. We're open for questions now.
So, Andrew, the first question we do have here for you is, can you offer any suggestions for practical and efficient management of the load associated with outdoor air introduced to satisfy the NCC requirements for ventilation of refrigerated room?
Now, obviously, when you have people, especially in production area, which is our refrigerated spaces, under the ventilation standard, you need to introduce the outside. So there's something that you have to sort of take into account of the latent component of the outside air being introduced into the room. So obviously you will have larger latent load component of your evaporator. I hope I answered that question if that's there. Yeah.
Thanks, Andrew. Another question here is, where can you find more reference material on some of the stuff that you presented to us?
I think on the very last slide, which I did not read out, was the one from
this one here.
Yeah, this one here. Yeah. So those formulas coming from two sources. Actually, refrigeration handbook, the ASI version chapter 12, and the other formulas coming from a publication from Massey University, Department of Biotechnology. They also run I don't know whether they're still running, a course called Cost-Effective Refrigeration. And in fact, many years back when they developed this, there was a software program called REDS that, I could say, with software makes your job easier rather than calculate it from principle and just input whatever is required. And that's the, but unfortunately, as I say, that software is no longer available.
Yeah, thanks, Andrew. Next question we've got here is, what is a typical value for decimal portion for the average air interchange heat load calculation, and how is this determined?
Well, depending on how heavy the forklift truck in and out. All right, so all this is just an estimation.
Okay. Yep.
Got to minimize by using rapid closed door and air curtains and so on. But other ways, because there's a source of, as I say, latent load, and that's also bringing moisture into the room, and you need to defrost the evaporators in freezers a lot more often as well.
Yep, sure. Next question we have here is, do you have a typical percentage of the various heat loads for a standard small cool room for restaurants?
As I said, these days there are, for restaurants and so on, the software programs, the commercial software programs available, rather than go by rule of thumb, so many watts per square meter. I don't think that's in air conditioning. That's what often is done, but not in refrigeration room. I don't think it all depends on what's been stored in the room. Is a door opening? So I think trying to use so many watts per square meter, I don't think that's a reliable guide. Hope I answer your question.
Yep, thank you. Next question we have here is from George, who's asking, why is the defrost system efficiency too low, i.e. in the range of 0.2 or 0.3? How can we increase the defrost system efficiency?
As I said, that formula came from the publication from the Massey University, I think, and I think it's probably an arbitrary figure. So, and as I say, it's a load estimation, so it will vary. So I think often it's just judgment more than anything else, and every room's application is different. So I think we just have to do a judgment in terms of that fraction. But the formula is only a guide.
Yeah, thank you, Andrew. And another one here is, do you recommend performing air leakage testing for cold freezer rooms as part of commissioning? If so, any particular air leakage rates at certain pressures as good practice can be used?
For air conditioning, yes, it's standard practice, but I'm not aware that this is used for freezers and so on. But Jonathan, maybe you can help me out on that. He said, I know air conditioning, it is a practice, but for cool room and freezers, have you seen that been applied to air leakage tests?
Generally, the only time we see air leakage tests is on large industrial plants, particularly ones that are going to have CA infrastructure or controlled atmosphere for, say, long storage of fruit and vegetables. Other than that, generally, no, we don't see that.
No, yeah. Thanks for answering that, Jonathan. Yeah.
Thanks, Jonathan. Thanks, Andrew. So another one we've got here from Peter, who's asking, how do you introduce outside air into a freezer? He was asked recently by a client, so just wants to ask that one.
Outside air into the freezer, because a freezer is not a really comfortable working space, and usually people do not stay in a freezer for long. And you got forklift truck drivers in and out, and also these days now a lot of large installation now is all automatic material handling, and so in fact there's no people go in the room, and that will also minimize the small opening for product to go in and out automatically. Using fresh air in the freezer, again, I'm not aware of. Jonathan, can you answer that question? You come across ventilating freezer rooms for people working in the room as a requirement under 1668, Part 1.
Generally, there aren't a lot of times when the freezer room is classified as an occupied space. Most of the time, freezer rooms don't fall under that category. So I've never come across one that requires fresh air for people working there all the time. Otherwise, yeah, you just have to work through, as Andy said earlier, with respect to introducing air via outside air and just accounting for the additional latent heat loads that comes from, and sensible loads that comes from that.
Yeah, as I say, I've not heard of that yet.
Yep, thank you both. Next one we've got here is, could you please let me know how I can calculate the heat gain in a cool tank inside attached with a chiller, is one of the questions.
Obviously, you need to know the type of insulated material for the tank. As I say, what material is used. So mainly your heat transmit. I'll assume it's a closed tank. So it's really the heat flow in will be due to the temperature difference inside and outside the tank. If it's an open tank, it would be quite a different thing because of your evaporation rate and so on in an open tank.
Yeah, the question was, how can you calculate the heat gain in a cool tank inside attached with a chiller?
Just of heat gain of the tank itself, you just have to go back to first principles, like what Andy was talking about, the same as the room. Obviously, it'll be different inputs to that equation with respect to the air versus water, but you'll have the thermal coefficients of the tank, the walls of the tank, the insulation of the tank wall, and you work it out that way. You'd have to have some indication of what the tank is made out of and the temperatures inside the tank, outside the tank, and go from there.
And assume it's also a closed tank, not an open tank as well.
Yeah. Thanks for that. So next question here we've got is from Jason, who's asking, do you recommend air curtains in front of freezers or cold rooms to minimize air interchange?
Sorry, I wasn't paying attention for a minute.
That's okay. So Jason is asking, do you recommend air curtains in front of freezers or cold rooms to minimize air interchange?
I mean, it will help, and also, I said, rapid roll doors, and again, depending how critical it is, and so on. And so another way is to use chemical dehumidification to minimize forcing on evaporators inside a freezer. And also the design of the empty room as well. Getting rid of the moisture outside the freezer. So it's good practice to have an empty room rather than it's like a truck loading straight into, without empty room directly in the freezer that brings in warm air. So these are the design consideration and layout of the freezers. That's my answer.
Yeah. Okay, so next one we've got here is, do you need to comply with AS 1668.2 for ventilation of occupied space?
For unoccupied space, no. If it's occupied space, yes, you have to put, allow for. Yeah. Or the other thing is maybe use CO2 sensors to minimize the amount of outside coming into.
Yeah, brilliant. Next one we've got here is, what is the most common refrigerant used and what is proposed for more suitable refrigerants?
I think so.
Sustainable refrigerants. Sorry, I'll say that again. So what is the most common refrigerant used and what is proposed for more sustainable refrigerants?
On large refrigerant warehouses, obviously, as I say, ammonia, and now I think CO2 in some cases, but we really haven't seen any large cold store here using ammonia. I've seen it in New Zealand using CO2. And now ammonia for big cold stores and so on is low charge ammonia, which can take have a niche market there. And now for smaller rooms and so on, I think we still see a lot of synthetic refrigerant being used because of the cost. So to be more sustainable, obviously ammonia and CO2, obviously won't go down that way, but cost and so on. Could be, as I said, small cool operators always look at the cheapest rather than sustainability.
Yep, thanks, Andrew. Next one here is from Stephen, who's asking, how is condensation in ceiling spaces addressed in cold room spaces?
Sorry, can I lapse of concentrate? Can you repeat that again?
Yeah, sure. So the question here from Stephen is, how is condensation in ceiling spaces addressed in cool room spaces?
Again, as I said, to minimize condensation, as I said, obviously the water vapor will eventually find its way into the evaporator. The evaporator is a colder surface, so you condense it on the evaporator. So if it's condensating on the ceiling space, I think there must be something wrong with the integrity of the ceiling insulation for it to condensate, because as I said, the moisture, the water vapor will go to the coldest. It's all to do with the dew point of the air in the room. That's what causes the condensation. Right? We look at the psychrometrics of the air in the room, the temperature, humidity, and so on.
Yep. So next one we've got here from Erica is, you mentioned you pay for evaporator fan energy in your presentation, but what efficiency features would you recommend for these fans?
Oh, obviously, you want the highest efficiency of the fan, and also if you can avoid blast freezing, or go to plate freezing, and then you eliminate the fan as a heat source. So obviously, to go to plate freezing, your capital cost goes up. So you've got a balance between operating costs and capital costs.
Yep. Next one here is, do you typically insulate the condensation drain pipe due to a very low temperature of condensation?
Yeah, all the condensate drain pipe would need not only be insulated, I think they should be heat traced as well to prevent ice forming inside. If it's ice from inside the pipe, then you got problem. Then with the water overflowing and getting into a floor, they become a safety hazard. So yeah, so all drain condensate pipe should be always clear of ice. So by heating, I think insulation will not good enough, and also the integrity of insulation deteriorates as well over time.
Thank you. Next question. How can energy efficiency be optimized?
Well, I think we have to look at how we can minimize all those sources of heat that we just learned this morning. So as with lighting, which nowadays LED lights that we're using instead of fluorescent or incandescent light, and obviously, as I say, the other one is air movement in there. So and also humidity. I think these are all and as I say, insulating material, what type of insulating material and so on. And so I think it's many look at each of those components, how we can reduce each of those components.
Yeah, thank you. Next one here is, can you please address the pull down time for bringing product temperature down from entering temperature to final product temperature and how this impacts the heat load?
It all depends on batch production and so on. And the chilling time, there are formulas quite complex that you can set up and so on. So it's something, as I say, it varies depending on if your production thing is. So the form, I mean, you can probably software, as I say, previously read in that software program looks at freezing time, how long to freeze this product, and depend again what sort of product. So yeah, so all depends, as I say, on the production type of product and how long it takes to chill and freeze. All those are factors. Yeah.
Yeah, great. And thank you everyone for your questions coming through. There is a lot, so we'll do our best to get through them. Next one here is refrigerant safety limit a concern inside the cool room, considering it is occupied for short periods?
With synthetic refrigerant, it's non-toxic and so on, but if it's CO2 being used, obviously you need to have sensors in. And now putting sensors in cool rooms probably much easier than in freezers, because whatever the sensors in the room for refrigerant detections will affect the operation. Jonathan, would you like to add to that one? Yeah.
I think, yeah, for every refrigerant, it doesn't matter the safety classification. You still need to take into account the RCL. It's just the reality that most of the synthetic refrigerants systems aren't big enough to sort of quantify that amount of refrigerant in an enclosed space, but it still should be taken into account, you know.
Yeah, and it'll also depend on the density of the refrigerant. Like ammonia is lighter than air, with other refrigerants, the synthetic are heavier in the air. So yeah, so it depends on what's the volume of refrigerant coming into the refrigerated space. Yeah. In comparison to the volume of air in that room as well. So what's the concentration? So,
yeah, thank you. Next one here is, how do different types of foods stored or pulled down of low times have an effect on calculated refrigerant capacity? Are there any equations to determine this?
As I said, with formula and so on, this will all depend on specific heat, which in terms depending on the water content, fat content, and so on. So different product with different specific heat. And can you repeat the other part of the question, Marie, please? Yeah. Equation, can you repeat that again after trying to...
Yeah, sure. I'm just, sorry, there's a lot of questions. I'm just trying to read through them. So I'm just trying to find it. Well, I might have to come back to that one, Andrew.
I'm just part of it. I didn't think I answered.
There's a lot of questions. So next one we've got here for you, Andrew, is inverter compressor common in the refrigeration units, and can it save energy in big amounts?
Jonathan, have you come across that type of compressors being used? Or scroll compressors? I wasn't sure whether you
can get variable speed units now. Yes, well, and the amount that you save, you will save something. You will get better performance with more stable suction pressure, but how much you save will certainly depend on the system and the use. You know, freezer, chiller, and all the variables.
Yeah, great. Thanks, Jonathan. Another one we've got here is, are there any means of monitoring or alarming methods to find any condensation freezing inside the condensate drain pipe?
Not I know of. Jonathan, will I answer that question?
Can you just say that one again, Marie?
Yeah, sure. Any means of monitoring or alarming methods to find any condensation freezing inside the condensate drain pipe?
No, not at this stage. The best method is, as Andy said before, is to just insulate and heat trace. That's the best thing to do. Yeah, you'll know once it backs up through into the drip tray.
Yeah, great. Next question. Do you include the component of heat from the heat trace element that is inside the condensate drain pipe inside the cool room? Is the heat load flax? What that is?
Yeah, usually the heat trace element, the heat for is insignificant, but because it is also insulated as well, So, and if it's lots of them, and the heat tracing of high voltage, then I think it will contribute, but I think probably it is insignificant. Yeah.
Yep, sure.
Size of the room as well. Yeah.
Yep, no problem. Next one here from Andrew is, why isn't the defrost cycle of cold rooms, so hot gas bypass defrost, not considered in the heat load calculation and only freezer rooms?
Well, chillers often we use off-cycle defrost for that reason. Because when the room is down to temperature, we stop the flow of refrigeration into the room and just allow the fan to circulate, warms the air, and as the air warms up, it will be enough to melt any frost accumulating on the surface. And because, as I say, the cooling is not 24 hours, it'll be on and off cycle, so the off cycle time will be enough to get rid of the frost building up on cool rooms. So sometimes cool rooms called chillers. Yeah. Yeah,
sure. Next one here is, what's a pragmatic approach for sizing the system? How much allowance on or safety factor for peak times and peak loads, etc.?
Again, it's for judgment. A lot of people use 10-20% as a safety factor. And now the other thing is the software that are often used. They do use a safety factor, but again, I think it's judgment as well, yeah, and experience, I think.
Yeah, thank you. Next one, Andrew, is how do you consider after defrost load? Considering equipment will be operating at different conditions compared to normal operation?
So often you got multiple evaporators in the room too, but not in a large room, so they're not all defrosted at the same time. So as I say, one might be defrosting and others are still operating. So obviously the one defrosting will be imposing a heat load on the other operating evaporators. Yeah. So it's more the case, because otherwise the room temperature goes up and go out of spec. Whether it's desirable for the product is another thing.
Yeah, sure. So next question here is based around sunlight. So how do you estimate the load of a room that has full or partial exposure to direct sunlight for all or part of throughout the day?
I think if it's completely exposed to the sunlight, which again depending on cold room construction of the cold room, often the room is inside building. So but if it's completely exposed, including the ceiling, often the walls are exposed, but not the ceiling. And so you will probably treat it more like an air conditioning building, when you look at the time of the year, the angle, and so on. It's more of a commercial building, the type. But yeah.
Yeah. Yep, great, thank you. Next question here is, what would be some points to consider for cold or dry stores for archive stores?
So I think the thing is what sort of humidity is required in an archive store, right? So, so obviously, the design of the evaporator, determine the, as I say, humidity or the other way around. the humidity required to determine the design of the evaporator coil.
Yeah, sure. Thank you. What are the typical type of fans used inside the cool rooms to distribute the airflow?
So now it depends again on obviously we're going for the most efficient fan. In recent years, the type of fan design in terms of the blade design varies as well, and also whether the evaporator is mounted inside the room or could be mounted in large system. Cold stores now, the evaporator mounted in alcoves or in penthouses, so the type of fan used could be different. So they mostly axial type fan rather than the centrifugal type fan. So I hope I answered that question.
Yeah, thank you. Next one is, what are the basic equipment selection criteria and guides and reference documents for freezer rooms, such as duty or standby or redundancy?
Obviously, with redundancy increases the capital cost, and often for large processing plant, large refrigerated warehouses, they normally would have what they call swing compressor. So the compressor, especially got both chilling application and freezing application. So you got one compressor can either work as a low stage or high stage. I hope I answered the question, if I either answered the question correctly. Yeah.
Thank you. Next one here is there any commercially available heat load calculation software for cold rooms that can be obtained by consultant engineers?
There are many available. Next week, I think there's a session on by Defrost, if I'm not wrong. And there are many also equipment manufacturers and so on. And then you got the Danish Technical Institute one. Jonathan, what's the name of it? Just off my mind. Coolpack. Yeah. Is that right? Coolpack?
Yeah, Coolpack.
And other software that you use for load estimating?
Excel works well.
Yeah, you do your own. Yeah, develop your Excel. Yeah.
Yep.
Software available. Yes. Yeah.
Yep. Brilliant. Next one we've got here is there any regulation requirements to have an electrical isolator inside the room adjacent to the evaporator?
It's certain. Fan isolation, if that's the question. Yeah. And I'm not aware that it's a regulation. Jonathan? I think if I read the questions correctly. Is that Jonathan about isolation? I think of
Can you read that one again? Right?
Yeah, sure. Is there any regulation requirements to have an electrical isolator inside the room adjacent to the evaporator?
Generally, we do have isolators for fans in the room, but that is site specific. Yeah, depends on the electrical installation and where the switchboards are located and the like.
Yeah, there's no regulation as such, really. It depends on client's requirement. I mean, from safety point of view, for isolation, I would recommend putting an isolator for your fan for people to work on. Yeah.
Yeah, sure. Another one here is how is the volumetric airflow of traffic into a room calculated for the instantaneous heat load for the air interchange?
I think, as I said, there were two formulas early on. one for instantaneous, as I say, the volumetric airflow of your door, and also the forklift, because you got forklift, because of the dimension of the forklift, that obviously reduces the opening. So you got that fraction there, I think, to consider.
Yep. Another one here is, why isn't the efficiency of electrical and mechanical devices not considered, and the just rated kilowatts of these items used as their heat load?
And the other one, because you go by the size of electric motors operating those equipment, again, depends how often they're being used, so you might have to apply a diversity factor there. What to say, they're not continuously being operated unless they are.
Yeah, sure. Another question here is, do cool rooms have a safety latch on the door to prevent persons from being locked inside?
Well, yeah, this is, you look at the standard, there's a requirement so that nobody can be locked in there. So whatever mechanism you use, it could have a padlock outside. Internally, mechanism should be able to be dismantle and open the door. I think that's also in the National Building Code as well. Is that right, Jonathan? Yeah.
Yes, that's correct. Yeah, or you can have a trapped personnel alarm.
Yeah, personnel.
Yeah.
Somebody press a buzzer and the siren or the flashing light comes on. Yeah.
Yep, brilliant. Well, I think that is all the questions that we have received there, Andrew. So well done on getting through all those questions, and thank you very much. So everyone, that does bring us now to the end of today's session. So I'd just like to thank everyone who's attended. A special thanks to Andrew for delivering today's session. And of course, a special thank you to members of AIRAH Refrigeration Special Technical Group who've assisted in putting all of this together for us. A recording from today's session will be made available for viewing on the AIRAH website, and I will let you know when that does become available, hopefully within the next couple of weeks. A special thanks goes to our industry supporter, Kirby, who helps us put these great sessions available for you all. So should you wish to register or learn more about the other upcoming sessions that we've got in this series, please visit the AIRAH website for more information and links to register. Should you wish to be involved in AIRAH's refrigeration special technical group, please don't hesitate to get in contact with me, and we'll be more than happy to get you involved. So until next time, until you join us in our next session, thank you all again for your time. Thank you very much, Andrew, again for your presentation, and everyone take care until the next time I see you join us.